Let's take a look at the spontaneous redox reaction. Taking a strip of zinc metal and placing it into a solution of copper 2 sulfate. The copper 2 ions are going to come in contact with the zinc metal and would gain 2 electrons from the zinc atom. Copper then, by gaining 2 electrons, has undergone reduction. And the zinc, by losing 2 electrons, has undergone oxidation. As the reaction proceeds, the zinc metal is going to dissolve, and the copper ions are going to come out of solution and plate onto the zinc as copper metal. And so you'll see the solution start to get a little bit less blue as the copper ions come out of the solution. This dark stuff that you see here is actually the copper metal then plating onto that piece of zinc. The zinc, meanwhile, while it's losing electrons to copper, goes into the solution. Now, if we could take this whole process and have those electrons, rather than being transferred directly in the solution here, if we could have them take place through an external pathway, instead of directly between the reactants, then we can take that energy that's being produced in that spontaneous redox reaction and have it perform electrical work. And we would do this by use of a voltaic or galvanic cell. So now we have 2 compartments. This one containing our copper sulfate and a piece of copper metal or a copper electrode. And this one contains a solution of zinc sulfate and a piece of zinc metal or a zinc electrode. The 2 sides are connected by a porous glass disc, which allows contact between the 2 solutions. And you can see that the 2 metal electrodes are connected to a voltmeter, which reads the potential of the cell. This is what a typical voltaic cell looks like. This is called a salt bridge, and it takes the place of the porous disc that we saw in the previous arrangement that allows contact between the 2 compartments. Zinc is losing electrons, and of course loss of electrons is oxidation. Oxidation occurs at the anode, and note that both of these letters, O and A, are vowels. So this is our anode. Copper is undergoing reduction because it's gaining the electrons, and reduction occurs at the cathode. So this is our copper cathode. Notice that cathode and reduction are both consonants. This is called the cathode because cations are going to move toward it, like our copper cations. And this is called the anode because anions are going to move toward it, like our nitrate ions. Now, as soon as an electron moves from this compartment through to this compartment, we now have an unbalanced charge in each beaker. And so electrons would cease to move across once the charges were unbalanced. That's the purpose of the salt bridge. As zinc loses electrons, it forms zinc ions with a +2 charge that move into the solution. As the copper is gaining the electrons, the copper ions are forming solid copper molecules. And so the addition of the negatively charged electrons to this compartment would cause the nitrate ions to move through the salt bridge towards this compartment towards the positively charged zinc that is in solution here, and thereby balancing out the charges in both compartments and allowing the circuit to be complete. So why do electrons transfer spontaneously from a zinc atom to a copper 2 ion spontaneously the way they do? Well, the flow of electrons going from the anode to the cathode of a voltaic cell is kind of like the flow of water going over a waterfall. The reason that water flows over the waterfall is because the potential energy is lower at the bottom of the falls than it is at the top. In a voltaic cell, if we have an electrical connection between the anode and the cathode, the electrons are going to flow from the anode to the cathode in order to lower their potential energy. The potential difference between the anode and the cathode in a cell is called the EMF. It's electromotive force. It's also called the cell potential and is designated as E cell. It's often referred to as cell voltage. And for any cell reaction that proceeds spontaneously, like the one in the voltaic cell example that we took a look at, the cell potential will be a positive value. And the cell potential of a particular voltaic cell is going to be dependent on a few things. For example, what exactly is the reaction that's taking place at the cathode and at the anode, and what are the concentrations of the reactants in the products, and at what temperature are we at? First, we'll be looking at cells that operate at 25 degrees Celsius, which we consider to be standard conditions for electrochemical cells. And also for standard conditions, we'll consider any solutions to be 1 molar concentrations for both the reactants and the products, and also at a pressure of 1 atmosphere. And so under those conditions then, the EMF is called the standard EMF, or the standard cell potential. Here we have a table of standard reduction potentials that have already been determined for us. And since every voltaic cell involves 2 half cells, it's not possible to measure the standard reduction potential of a half reaction directly. But if we have these standard reduction potentials for a particular half reaction, then we could determine what the standard reduction potential of the other half reactions relative to a reference half reaction. And that reference half reaction is the reduction of hydrogen ions to hydrogen gas under standard conditions, which we assign a standard reduction potential of exactly 0 volts. And so an electrode was designed to produce that half reaction, and it's called a standard hydrogen electrode, where we have a piece of platinum wire, and remember that platinum is super unreactive. It's connected to a piece of platinum foil that's covered with platinum atoms, and that serves as an unreactive or inert surface for the reaction to take place. And the whole thing is encased in a glass tube so that the hydrogen can bubble over the platinum under standard conditions. It's important to note that whenever we assign a potential to a half reaction, we write the reaction as a reduction. So in our example, since the zinc is undergoing oxidation, this is what our half reaction would look like. And if you take a look at table 20.1 on page 863, or at the previous slide, you'll see if you take that oxidation half reaction and flip it around to a reduction half reaction, then you would find the reduction potential to be negative 0.76 volts. And since this is the reverse of that, this is oxidation, then our E would be a positive 0.76 volt. And since it's the copper ions that are gaining electrons or being reduced, the half reaction for the copper ions would be having a reduction potential of 0.34 volts. And since cell potential is calculated by subtracting the reduction from the anode from the reduction from the cathode, we get a cell potential for that process of a positive 1.10 volts. And since I neglected to mention it earlier, 1 volt is the potential difference required to impart 1 joule of energy to a charge of 1 coulomb. And remember from way back when that a coulomb or rather, one electron has a charge of 1.60 times 10 to the negative 19th coulombs. And that positive value tells us that that cell reaction would proceed spontaneously. So just like our potential energy is highest at the top of the waterfall, we relate that to our cell potentials. And the more positive the value of the reduction potential, then the greater the driving force for reduction. Gain of electrons is reduction. And we know fluorine is the most electronegative of the elements on the periodic table. And so it undergoes reduction or gain of electrons very easily. Metals have a tendency to lose electrons and undergo oxidation. So their reduction potentials then are going to be very negative.